In today's video, I want to talk about how carboxylic acid derivatives can be used in synthesis. And the first example I want to talk about is the use of carboxylic acid derivatives in the synthesis of primary amines. Secondary and tertiary amines can be generated easily during using an SN2 reaction, but primary amines are more difficult. You might think that you could take ammonia and treat it with an alkyl bromide and get a primary amine. And the first part of that reaction is true. You're going to treat ammonia, which can act as a nucleophile and attack the alkyl halide and form a primary amine. Unfortunately, this primary amine is more reactive towards alkyl halides than ammonia is. And so rather than ammonia continuing to react with that alkyl halide, the ethylamine is going to attack the alkyl halide. And so you get a secondary amine, which is also reactive towards alkyl halides. And you can get a tertiary amine. And so if you try to use SN2 chemistry to produce a primary amine, you're going to get a mixture of products that include the primary amine, but also have secondary and tertiary amines as well. So in order to synthesize exclusively the primary amine, you can use an imide in the Gabriel synthesis. So an imide is essentially the nitrogen analog of an anhydride. And so here we have a carbonyl on either side of an NH. So that is the nitrogen analog of an anhydride. And this particular one is known as phthalimide. And it is often used in the Gabriel synthesis. So in the first step of the Gabriel synthesis, you take phthalimide and you treat it with sodium hydroxide. And that's going to deprotonate the nitrogen to give you this anionic compound. And that negative charge is resonance stabilized, so this can kick over here and the electrons can kick up to oxygen to form this structure. And the equivalent structure where this oxygen gets the negative charge is also available. In the next step, you are going to treat that anionic compound with an alkyl halide. In this case, we have butyl bromide. And the anionic nitrogen is going to replace the bromine. And so we wind up with this compound. The third step is the acid catalyzed hydrolysis of an imide. The mechanism would look very similar to that of the hydrolysis of an amide. You've just got to go through it twice to break both carbon-nitrogen bonds. And because you're under acidic conditions, rather than getting an amine, you're going to get a protonated ammonium salt. You have 3 protons on a primary amine. And then in the last step, you're going to treat it with sodium hydroxide again, and that is going to deprotonate the ammonium salt to give you a primary amine as the final product. Nitriles are a carboxylic acid derivative that it's sometimes hard to see. But carboxylic acid derivatives get their names because you can hydrolyze them to form a carboxylic acid. And in fact, a nitrile can be hydrolyzed under acidic conditions to form a carboxylic acid. And so when you do that, the first step is to protonate the nitrogen of the nitrile. And you get a protonated nitrogen with a positive charge. We've got water floating around now. And so water is going to come in and attack the partial positive of the carbon attached to the nitrogen, and that's going to kick up one of the pi bonds in the triple bond up to nitrogen, which leaves this compound. We're going to do a proton transfer. Most of this is an equilibrium at this point. Water is likely the best base in solution, and so I'm going to use water. And deprotonate it. And then I'm going to use my newly formed H3O plus to protonate the nitrogen again. And this thing has resonance. There's some electrons here that can kick down and kick over. And then again, water is likely the best base. It's going to come in and remove that proton, which is going to give an amide. And this compound is an amide, and we've already seen that amides can be hydrolyzed under acidic conditions to form a carboxylic acid. And so this is multiple reactions, or multiple steps, I should say. But it goes all the way to a carboxylic acid. And in this case, a protonated ammonia. Because nitriles can be easily synthesized using sodium cyanide and an alkyl halide in an SN2 type reaction, they can be super useful in synthesis. So if I start with an alkyl halide and sodium cyanide, this just does an SN2 type reaction and displaces bromide to form this nitrile. And we just saw that this can be hydrolyzed to form the carboxylic acid. We've also seen previously that nitriles can be reduced using rainy nickel and H2 to form primary amines. So we've now seen two different ways that you can form primary amines in good yields, one from a nitrile and one using the Gabriel synthesis. And now using nitriles, we have a good way to form carboxylic acids as well. When we first introduced carboxylic acid derivatives, we started with acid chlorides as a good way, or as the most reactive carboxylic acid derivative, in that they can be converted into many different varieties of carboxylic acid derivatives. But we don't know how to make one yet, so that we could then use it in synthesis. And so let's take a look at how chemists activate a carboxylic acid to make an acid chloride, which can then be used in synthesis. So when we converted an OH of an alcohol into alkyl chloride, we use thionyl chloride. We can also use thionyl chloride to convert the OH of a carboxylic acid into a chloride. And so in the first step of this reaction, the oxygen acts like a nucleophile and attacks sulfur, which kicks some electrons up to form this intermediate. The electrons on oxygen can kick back down to sulfur, and that's going to kick off a Cl. I forgot a positive charge on that oxygen. And that is going to form this compound. Some base is going to come in and deprotonate this. It's unclear what the best thing in solution right now is. Maybe the Cl- that we just formed. Maybe another thionyl chloride could come in and deprotonate that. But some base is going to come in and deprotonate to give this compound. And then the Cl- is going to come in and attack to form the tetrahedral intermediate. Which then collapses to kick off SO2 gas and a Cl-. And so this final product, the acid chloride, is more reactive than the starting carboxylic acid. But because in this reaction we form SO2 gas and the gas leaves, this is a driving force to form the more reactive acid chloride as opposed to the less reactive carboxylic acid. Another reagent we use to convert the OH of an alcohol into a chloride is phosphorus trichloride. which can also be used to convert the OH of a carboxylic acid into a chloride. And so in this case, the alcohol attacks the phosphorus, and that's going to kick off one of these Cl's and form this compound. And this HOPCl2 is a good leaving group. And so I can attack the carbonyl with Cl- and create a tetrahedral intermediate. And this tetrahedral intermediate will collapse to kick off this compound here. And that is another good way to form acid chlorides from carboxylic acids. The last use of carboxylic acid derivatives in synthesis I want to talk about is the creation of an anhydride, which can then be used to form other carbon-carbon or carbon heteroatom bonds. And it turns out that if you heat an anhydride, if I'm going to balance this equation, I'm going to need two anhydrides, or two carboxylic acids. I can form an anhydride plus water. So essentially, I have lost the OH of one carboxylic acid and the H of another and stuck them together to form water and an anhydride. And if I add heat, this equilibrium sets up and I can form the anhydride. If I want to favor the anhydride, if I want to produce this product in good yields, one way to do that, or to perturb the equilibrium, is to come up with a way to remove water. And so one classic way to remove water in a chemical reaction, in organic anyway, is to use a Dean-Stark trap. Which we saw in lab and can remove water. Another way is to use a chemical dehydrating agent, and the most common is phosphorus pentoxide, P2O5. And so if you were to write or want to synthesize an anhydride, you could take a carboxylic acid. You're going to need two equivalents of that. And you're going to heat it in the presence of phosphorus pentoxide. And that is going to result in this anhydride being formed as your primary organic product. I think we'll wrap up today's video here, and we'll pick up with how you might use some of this in synthesis next time.